Hey folks, two quick video segments coming to you from chapter 11. Only one of which we actually need for Tuesday's worksheet. There's one worksheet, so that video segment, I imagine, is something that you'll refer to while you're working on that worksheet. There's only two worksheets tomorrow, or Tuesday, so there should be time to do that. We already have Newton's second law in the linear case. But now that we're here in chapter 10, we can talk about the dynamics of rotation using Newton's second law for angular situations. The sum of the torques is equal to the moment of inertia times the angular acceleration. There's a word that we've used a couple times in the context of Newton's second law, and that is equilibrium. For example, we talked about Throckmorton, and we said that at all times through the swing, Throckmorton is in equilibrium, not accelerating, just moving slowly. So let's put a little bit of a finer point on equilibrium. And that's what chapter 11 is all about, equilibrium. What we mean when we say in static equilibrium is that the sum of the forces is equal to 0, and that the sum of the torques is also equal to 0. So if this object or system is not moving, it will stay that way. If it is not rotating, it will stay that way. If it is moving, it will stay that way with that velocity. If it is rotating, it will stay that way with that angular velocity. That's the story. That's equilibrium. And on Wednesday and Thursday, we're going to apply these conditions. And what this really means, that there's sort of consequences that inform our problem-solving strategy. We can almost, well, this equation means not only is the sum of the forces vector-wise equal to 0, but the sum of the forces in the x direction must be the sum of the forces in the y direction must be the sum of the forces in the z direction, all equal to 0. Each of them is equal to 0, and it's like three separate equations that we have to sort of leverage to talk about variables that we don't know. The sum of the forces in the x direction must be 0 in order for this to be true. The sum of the forces in the y direction, the sum of the forces in the z direction, each have to be 0 in order for this to be true. And in order for this to be true, we are almost always talking about possible rotation in a given plane. So we're either talking about clockwise or counterclockwise. So the vector part is largely irrelevant. It's perpendicular to the plane in which we are considering possible rotation. And it's either positive or negative, depending whether we're talking about clockwise or counterclockwise. So I'm going to lose the vector. But if it is true that the sum of the torques is 0 and that it isn't going to rotate, it must be true that that's about any axis we like. So we have a lot of freedom to choose any hypothetical point around which a thing could rotate. and talk about the fact that the sum of the torques about an axis through that point should still equal 0 because it's not rotating around that point. Or at least it's not accelerating around that point angularly. And the other nice thing about that is that this lets us generate multiple equations. Pick a different axis, we can generate a different equation for that, the fact that the sum of all the torques acting must still be equal to 0 around that axis, again, because the thing is in equilibrium altogether. Let me show you a quick example. What we've got is a floor and a wall that make a corner, and a ladder of length L and mass M. We'll say that it's a uniform ladder, so its center of mass is halfway along its length. And let's assume that the floor is frictional, but that the wall is frictionless. Maybe because we've amped up the friction at the bottom by putting like rubber feet on the bottom of the ladder or something. As you might know from experience, if we make theta too small, it'll slide. It'll slide down the wall and then it'll slam onto the floor. What angle theta should that be? Can we talk about the smallest possible angle theta? I'm going to modify our usual free body diagram because now when we're talking about torque, it matters where along the object the forces act. There's a normal force from the floor and a normal force from the wall. I'm going to call this one Fn and this one just Fw. There's the weight of the ladder. And there's the force of friction keeping it from sliding away from the wall. F, F, S. Static because we're talking about equilibrium. We want it not to slide. All right. So we write the sum of the forces in the x direction. And every equilibrium problem is going to go the same way. We start with sum of the forces in the x, sum of the forces in the y, sum of the torques. Almost always, we're talking about a two-dimensional thing, and we're x, y, sum of the torques. X, y, sum of the torques. Every time we're talking about an equilibrium problem. Sum of the forces, sum of the forces, sum of the torques. There are two horizontal forces, the force of friction in the positive direction and the force from the wall in the negative direction. I know neither of those things. I can talk about it in terms of mu s and the normal force. So I'm saving myself a variable, I guess. We'll have to see. Force from the wall equals 0. What else do we know? We know the sum of the forces in the y direction needs to also be equal to 0. There are 2 vertical forces. The normal force from the floor in up gravity in the down. And this is really nice. Okay, the normal force needs to be equal to mg. Okay, so with that information, we can plug that in here and say that mu s mg minus the force from the wall is equal to 0. But that doesn't let us talk about the angle. How do we get the angle involved? We need the torque equation. The sum of the torques acting on the ladder needs to be 0, otherwise it'll rotate, and we want it not to do that. We can choose any axis about which to consider the rotation that isn't happening. But if we consider the axis at which forces act, if we consider rotation about that point on the floor, the lever arm, the action distance to compute torque for the friction and the normal force, that action distance is 0. We gave them little tiny T-Rex arms and they can't exert any torque. It's like pushing on the door at the hinge. So if we talk about this point at the floor, there are 1, 2, 3, 4 forces that could exert torque, and I'm going to list them all. Torque from the normal force, torque from the force of static friction, torque from gravity, and torque from the wall. Now, about this axis, the normal force exerts 0 torque, and the force of friction exerts 0 torque because they act at the point of rotation, at the axis of rotation we're considering. The force of gravity, if the thing were to move in the direction that the force of gravity wants it to, it would rotate around this point clockwise. We use the minus sign because that's a clockwise torque. If the wall were to push it, it would rotate in the counterclockwise direction. So that's a positive torque in our convention. Okay, cool. Minus sign. Every torque, R, F, sine phi. The action distance, the magnitude of the force, and the sine of the angle between them. The action distance from the axis of rotation to gravity, L over 2. The magnitude of gravity, mg. And the angle between the radius vector and gravity. Is 90 plus theta. Plus the torque from the force from the wall. The action distance is the entire length L. The magnitude of the force, we don't know. Or, well, actually, I guess we do know. Oh, all right, I'll fix that in a second. And the sine of the angle between this to this, that angle is 180 minus theta. And that all adds up to 0. All right, so here, the force from the wall had better be equal to mu mg. So I will take that, plug that in here, and rewrite this equation so that we can manipulate it. Zero equals negative L over 2 mg. Now, sine of 90 plus theta. Well, let's see if we can get the sine of a sum is sine cosine plus cosine sine the other way, cosine sine. So sine of 90 plus theta is sine of 90 cosine theta. Plus cosine of 90, but cosine of 90 is 0, so this term goes away. Plus L. The force from the wall we said was mu mg. Sine of 180 degrees minus theta is actually just the sine of theta. All right, let's divide the entire equation by m. We can do that because we've got a 0 on this side. Let's divide the entire equation by g. Let's divide the entire equation by L. And let's move this guy to this side. 1/2 cosine theta equals mu sine theta. And if we want to solve for theta, sine over cosine is tangent. So theta gets us the arctan. So based on what the coefficient of friction is at the floor, we know the angle, the minimum angle at which we can orient the ladder. If it's any less steep than that, if it's any shallower an angle than that, friction can't do the job, it'll slide. That's the method. I know that was fast. Don't worry, we'll practice it, but I wanted to kind of illustrate what I was talking about. All right, next segment.